Okay, everyone, welcome to today's TITBIT from the organization MARLOG. We have a large panel of participants today, or not panelists, but we have many that have signed up for this presentation. So I'll use a couple of minutes to tell you a little bit about MARLOG and some of our offerings. MARLOG is the national Danish cluster for the maritime and logistics organizations and sectors, and we were established here at the 1st of January this year. But we have a long history of many years in the maritime industry and in the logistics areas. MARLOG has online events like today's TITBITs, but we are also sponsoring the World Maritime Technology Conference in April of 2022 from the 26th to the 28th. And I would encourage anybody that's interested and has the opportunity to sign up to participate there, where they can see many papers presented at a very high technical level, very similar to today's guest. And it's my distinct pleasure to welcome Josep Guerrero from the Center for Research on Microgrids, CROM at Aalborg University, where he'll tell us a little bit about microgrids. And I'm sure you also have a lot of questions and are very interested. I know I am. Josep, the floor is yours. Josep, you're muted.
Thank you very much for your introduction, Ernest, and thanks a lot for the Maritime and Logistics Innovation Denmark, MARLOG, to invite me for this talk. So here I'm going to talk about Maritime Microgrid Technologies for electrification of ships and seaports. And our Center for Research on Microgrids is placed in AAU Energy, Aalborg University here in Denmark. And you can find more information here. It will be displayed all the time, the website, and also you're welcome to contact me later on with the email. First, starting with the microgrid concept, we know from land-based systems that a microgrid is a small electric system that tries to generate, consume, and store all of them next each other in a sustainable way and considering geographical, social aspects and so on. This concept is right now exported to many other areas like water, food, and so on. And what I'm going to show here, it's a little bit beyond terrestrial applications, how we can go. Also, I want to thank my team. I know that some of the members of our team are connected right now. So thank you, because this presentation is also thanks to your contribution to our center, and this is important to say. Here are some pictures of the laboratories in AAU Energy, in which we developed microgrids for different applications, and we have hardware-in-the-loop solutions for different applications of those microgrid systems. We basically developed with power electronics converters and digital signal processors, solutions, control solutions, topological solutions. And the idea is always to have the electric part as smart meters, transformers, distribution, and power electronics converters to be physical real. And we try to emulate all the generation and load profiles, exactly what we do also in maritime systems. And here you can see that we can also develop multi-microgrid systems, which is also very important, as I will mention afterwards, and virtual power plants. And here is another picture in which you can see our lab facilities and the outside of our demonstration laboratories also. And also we have a very good collaboration as well with Typhoon Hill and the company Sonnen to develop the next generation of battery systems. So I think that's just one of the example of collaboration that we are running. So here are the different research frameworks of our center. One is multi-microgrid cluster. The other is digitalization, digital twins, and IoT and cybersecurity. Then we have also space microgrids, more looking on satellites, lunar bases, etc. And here what I'm going to talk is about maritime microgrids. But I will also introduce concepts regarding control at the beginning. So for instance, we talk recently a lot about artificial intelligence, but I'm not sure if we are aware how our brain works. And if we think about our brain, indeed, we have to be careful because we have 3 brains in our body. So we have first the part of the mind, which is connected with these 80,000 million neurons that we have in the brain. But then we have our heart, which have around 40,000 neurons. And then we have the digestion system with around 500 million neurons. So the same as a cat's brain, for instance. So really it's a totally distributed system, which is connected also by the spine, dorsal spine, and also the vagus nerves and so on. So indeed, it's very much distributed than we thought before, that it was just a centralized system. And then when we look inside this brain, we can also monitor the different waveforms. This is myself taking some samples of that. And another thing is that how much we can use of our brain. Indeed, we can use 100%. So it's not like we thought before that it's only 5% or something like this. We use indeed 100%, but simultaneously is only 2%, which is 4 watts due to glucose and oxygen limitation. However, normally we use similar neural network path, and that's why many people, they struggle to make changes in their behavior. But still, it's possible. You can see this is the 3-level model of a brain, which has been proposed by McLean. And you can see that indeed we have this part, which is the reptilian brain, which have 500 million years, which is more connected to the instinct, or the, let's say this is action-reaction brain that the reptilians develop. And then in the top of that, with 200 million years, we have the limbic brain, which is more connected to the emotional part and the feelings, which has been developed by mammals. And then we have the neocortex, especially this frontal part, which is the one who has been developed in the last 100,000 years by especially human beings, which is the one who's able to go to the future, come back to the present moment and take decisions. However, due to this amount of years, many times emotions are coming with decisions, and then the rational part, it's the one who comes with the justification. So we can see here that this 3-level control of the brain, we can see that we have in this part, the cerebellum, we have the supervised learning, and then this other part, the basal ganglia, is more related to reinforced learning with rewards, especially with dopamine. And then we have another level, the higher level, which is unsupervised learning. That indeed become a 3-level of control, very similar as we have today with microgrids, in which we have the primary control, which is very active reactive control to control voltages, active and reactive power. Secondary control to restore everything about the primary control. So this is more like the limbic brain. And then we have the tertiary control, which normally we have energy management systems, which are related to what I was calling the neocortex, right? So there is, it's amazing how we have this parallelism and how we can learn from that. And now focusing on the control of microgrids, I'm going to move forward with shipboard microgrids. So we know today that we have to reduce more and more emissions. And one way to reduce emissions is, of course, going more to electric. This is one way. And in that sense, the first ones were the Chinese, well, it was many other developments, but the first cargo ship, the biggest in the world, let's say, it was released in Guangzhou in 2017 with a 2.5 megawatt hour battery system. Then we can see also how the shipboard power systems architectures has been segregated. First, segregated plants, like having separate electric system, let's say the electric part and the propulsion part, like conventional cars. And then hybrids appear. And this was tremendous, especially with different kinds of ships, cruise vessels, drilling ships, OSVs, PSVs, LNG carriers, and so on. So you can see here, this is the main structure of a ship when going to electric, with the different diesel generators, power electronics converters, distribution system, and finally going through to the propellers. So one of the things that has been also changed, the idea is to merge the propulsion system and the service loads in only one, going to AC, so that efficiency improves a lot, and then going again to DC, because then we can interconnect here battery systems and make this frequency independent from the prime mover frequencies. So this gives us a lot of advantages, especially in efficiency, as I will explain later on. So here there's another picture from Typhoon Hill, in which you can see the different parts of this electric ship, the propellers, power electronics converters, diesel generators, more power converters, and the bidirectional power converter connected to battery storage. Yeah, and here we have the central control system. One of the earliest electric ships was the cruise ship Queen Elizabeth II, which, by the way, I will explain you later on. It had a failure, but one of the main disadvantages it was that it was only using one bus bar with 9 diesel generators. So a single bus bar, it's really a problem because of reliability issues. So right now, a major part of the ships have at least 2 separate buses, and those 2 separate buses are connected to a pair number of diesel generators. And then with transformers, normally, for instance, here you have delta Y transformer to eliminate the 5th, the 7th harmonics, and then you can go down to low voltage. You can see also here harmonic filters, which we will talk later on, especially when you move on to AC. Another important thing is that we have, according to this standard from IEEE, also what is called also notional AC zonal electric distribution system. So this means that a shipboard power system can be divided in number of zones. So this way we can disconnect those zones according to if there's a failure or some short circuit, we can just isolate it. That's something nice because we can see the shipboard power system like a multiple microgrid system. The same idea has been taken also for some other companies like Beacon Power, which is right now the Danfoss, having AC and DC grids inside the ship and having the number of conversions according to how is the nature of the loads and the generation that we need to couple with. So following the same example also, it was more at the beginning with the US Navy, they developed rings on DC in the level of 3.3 and 6.6 kilovolt, just to have higher propulsion system with increasing the efficiency by reducing the losses, and then having a number of microgrids by using the same standard. So also moving to DC is one of the things that are happening somehow. In that sense, you can see that when you have an AC shipboard power system, you have a number of diesel generators connected to the main AC switchboard. And then from here, we connect all of those to the transformers to eliminate harmonics. And then we have a double conversion with a back-to-back converter or a rectifier that moves from AC to DC and then from DC to AC. Right now, moving to DC with products like the one from Siemens, the Blue Drive Plus C, just to say one of the most successful one. The main AC main switchboard has been replaced by 2 boxes with a number of converters and then having the DC in the middle. Yeah, still we maintain the tiebreaker in the middle to disconnect if there's some event. This is just a picture from Siemens in which you can see the two boxes incorporating all the DC to AC and AC to DC converters in each of the sites. However, these have the problem that, of course, if the cables are having a little bit longer distance, then we can have losses. And to couple this, ABB came with another concept to have more integrated the power converters with the diesel generators and the motors. But however, as you can imagine, the DC bus voltage has to be increased to reduce the losses. So then, of course, DC breakers are more challenging than AC breakers. So that's also another challenge. So we maybe improve efficiency on the one hand, and we challenge protections. This is one of the pictures in that case from ABB trying to connect for long distance cables and having integrated those power converters with the propellers and together with the diesel generators. Why we move from AC to DC? If we work on AC, the frequency is fixed on 50 or 60 hertz. So that means that if we imagine that those diesel generators just one operation point, which is optimum, almost all the time will be working out of this optimum point. While if we work on DC, we just decouple the frequency of the synchronous generator, and then we can choose where to make the operation point. So we will obtain almost a flat response. Yeah, that's also from a review of one of our students here that she presented also how are the trends moving to medium voltage DC transmission lines, and which are the functional blocks and the main power converters. I don't have here time to explain it, but it's very good to look on this review paper, because we talk about the different radial distribution systems in which right now are the main part of nowadays electric ships, and how rings and also zonal distribution also into the picture. Another concept that has been also developed by ABB is the dynamic AC concept, which means, okay, we accept that we don't move to DC, but what we will do is to change the frequency of the whole of the main AC distribution system. So this means that we can change the frequency according to how much power we need. So we try to find an optimum point for the diesel generators. And then because we need to move again from AC to AC here, we have here the double conversion. And then for the hotel loads, we have our own dedicated converters. That seems to be fine. And the first data that ABB give us is that they can save up to 6% of fuel savings for large cruise vessels. That's for vessels of more than 20 megawatt. However, so far, still we don't know how it will be the impact with the design of the transformers, because the frequency is changing in a range. So still, this is one of the ideas that are in the table. We can see that also we have operational modes in which we could use in a regenerative way also the propellers. So that means that when the ship slows down, we could recover part of the energy, and with electric vehicles, for instance, and put back to the electric power system of the ship or to the batteries. That's why batteries are becoming also very important here. And I will talk a little bit about that. That's a picture of a platform super vessel. So you have to imagine that having more and more how this offshore industry is increasing, especially wind offshore wind industry. We need also to have more sustainable vessels. And in that sense, this is from a study made in Singapore, in which they took a PSV, converted from AC to DC. In that case, it was 1000 volt on DC. and they made some measurements. I believe that this data is from the Singapore laboratory in the university, but also together with Rolls-Royce. And in this figure, you can see that when you move to DC, you have almost a flat efficiency and flat losses, so flat efficiency for almost the whole operation points, which is much more improved when you compare which using feeds, speed, engine. So this means to fix the frequency and connect it directly. So still the question is, how are the losses from those converters affect the whole efficiency? And this is something that we in our center evaluate case by case. This is another nice example from Norway, the Viking Lady, which is an offshore supply vessel. And this OSV, they have been integrated also a DC bus together with fuel cells in order to manage the tunnel thrusters in one hand, and on the other hand also to support some part of the hotel loads. Yeah, it's not small, and it's also connected to a dual fuel LNG power plant as well. And then if we move to the control of shipboard microgrids, it's happening something similar as we have seen with terrestrial microgrids. So we have the three levels of control. You can see here the primary control. If we think about DC, it will be used for regulating, for the power sharing purposes, regulating the DC. And then we will have restoration. The restoration part will be on the secondary part, kind of the limbic brain that we talked before. And then everything about optimization algorithms, energy management system will be on this level. If someone wants to ask me about the power management system, probably it will be fine in the secondary level, because we need this level to be faster enough to take very fast decisions. And this is one of the examples that we took from another example. This is a 750 volt DC ship in which we implemented this multi-level control. And in this other ship here, you can see it was also implementing similar idea for an AC ship. This was a 4 synchronous generator shipboard power system. And in that case, what we studied is what happened if we can add, for instance, batteries and ultra caps in that sense. So here the idea was that for very fast response, we added ultra caps having droop controllers here, more flat, and then we added also battery systems with a less flat response and filter according to which is the frequency of cut-up that we wanted to coordinate the operation between diesel generators, batteries, and ultra caps. And then another important thing is when in a vessel we have dynamic positioning, then this is just one example from another platform in Norway. And here you can see the dynamic position. That's in this example, I believe it's from Brazil, in which we have not only the automatic control, but also the manual joystick. And those are based on very complex models, because finally the idea is simple, because we have wind models and then we have the thruster transformation and the controller and all the sensing from the position and heading measurements. But then normally what we need is Kalman filters to make estimation of all the position of the ship and what's going to happen there in the next seconds. Yeah. So what give us this information about the dynamic positioning is like measure part of the time. What we need, especially when we have heavy conditions, is that we need kind of a storage to be able to maintain this DP. Especially right now, we are talking about also DP4, which will be the next level of DP that we expect. And this is another example from an OSB. And this OSB, it has been performed, this DP. You can see that in that case, the DP, it's working 37% of the time with a demand of almost 2 megawatt. So that's very huge when we compare with the rest of the ship. And also, if we talk about protections, it's important also to bear in mind that we need kind of similar protections that we have in power systems. However, here it's a little bit more complex. So we need fast speed communications to coordinate all the IEDs, the intelligent electronic devices, which are connected to the different switch. And then we can see also the same trend with the Yatchs. So Yatch starts to be electric also. There's some companies, this is just one example from this company from Slovenia, but there's a number of them also going to full electric or hybrid. This is another project that we also participated with Taiwan, in which was the first hybrid electric ferry of Asia. So we are proud of this. We took out all the old engines and so on. We put power electronics converters from Vicedo, which is right now Danfoss. And this is the electric system, a couple of generators, the hotel loads. We passed from AC to DC. DC was 750 volt, a couple of propulsion motors, and a bidirectional converter, which was indeed an interlift boost converter. So it was the same power electronics that we use for the rest of the equipment, and around 100 kilowatt hour of a battery system. Yeah. So here you can see the batteries were provided by Superbee, and then we have a lot of more ferries going in Asia also, moving on this direction. Another project that we did also together with Poland, in that case in Gdynia, it was more to study the unbalance and also the harmonic, which was also performed. The harmonic part was performed in a PhD thesis of one of our group members. And it's, if you look on the case of Queen Mary II, it was basically the main problem was caused by harmonics. And what happened here is that the LCL filter that was installed to reduce harmonics finally caused that an explosion happened there. So that's why it's very important to take into account all the harmonics instabilities. Especially here, you can see the LCL filters connected to those converters, and here the capacitors. So that's a main issue that we need to take into account when we have especially rectifiers. This is just a diode rectifier bridge. Then you have huge harmonics, especially fifth, seventh harmonics are very important here. And that's why they are more and more, let's say, moving towards having LCL filters with IGBT control. And these are some of the measurements that our member took. So basically, you can see that when you increase active and reactive power, everything goes well. But however, the problem is what happened when we are reducing active power and reactive power is still high. You can see how also the number of harmonics are increasing. And increasing the number of harmonics have a huge impact, especially in shipboard power systems, because the challenge here is that inside our shipboard power system, we can have variations, for instance, of 1 hertz. So moving here from 60 hertz to 59.5 hertz. If we make an FFT to evaluate which are the harmonics, we obtain huge errors. However, if we are able, so here you can see here the spectral leakage. However, if we are able to implement new kind of methods that evaluate not only harmonics, but also interharmonics that may appear then we will be able to cope with better solutions than classical ones. And talking about solutions, what are the solutions that we propose for ships? We have, on the one hand, very expensive active power filters. And on the other hand, we have cheap but not very reliable passive power filters. So what we can see right now is that something comes in the middle, which are solutions that don't have to work, let's say, with high cost like active power filters, but it has maybe the possibilities of using, for instance, this kind of TRC solutions in which we can switch on and off inductors, but not with high frequency as happened with active power filters. We have been tested also this with our team members with some setups. For instance, we took the case of the Ferry in Taiwan to reduce harmonics in a simple way. And that's why you can see that a lot of standards are coming with saying about voltage transients, frequency transients, and maximum THD. Probably for naval applications, even THD is more restricted. They talk about 5%, while if we are talking about standard ships, 8% of THD is still acceptable, which is far beyond what we have in the grid. So this is one example that we took to study unbalanced conditions in ships. This was the Horizon 2 in Poland. You can see the ship and the engine room, and here is the control board with the diesel generator and the pump water, and this is the electric scheme. Yeah, that's a very conventional one. Here what we studied is that in normal conditions, everything it's fine, but however, when you have small imbalance in the shipboard microgrid, then starts to occur heavy spikes, especially here in the bow thruster. And that's why we start to be worried about imbalance here, because it was only 1.5%, which is, if you think about grid, let's say a terrestrial grid, 2% is still acceptable. So here is also very important. So probably that's also another phenomena that needs to study. And finally, because we have, not only because we have more electric ships, but also because when conventional ships are being connected to the port, are many times polluting the area because maybe they come with fish and they don't want to rotten it. They start their diesel generators, and that's why in many places, like this is a connection in the Rotterdam port, they start to connect the ships and to supply the electricity from the port. And that means that also this is a challenge for the ports, because especially when you think that the port is the one who has to support it, we have to decide which is the frequency and the voltage to be connected to the ship. And on the other hand, some of the ferries right now comes with their own battery packs. So we have to also be able to support them with something very similar as a CHAdeMO charging station with electric vehicles, using DC-DC converters that maybe are on the shore side. So probably DC configurations will be better for that, because the inverters can select the frequency and the voltage to be connected to the ship, and we can reduce something a little bit weird, like happened in this study, I believe also in Poland, in which they connect suddenly a ship to the port and a huge spike appear because of the inertia that the diesel generator internally has the ship. So that's why it's very important that we have converters on the other side that are trying to synchronize the port side with the ship to avoid these huge spikes. And another problem that we have here is about the port cranes, like we have here in our city, with a lot of cranes still still using diesel. And according to several studies, still you could recover part of the energy of those cranes when you lift down all those containers. Yeah? And according to those studies, we have seen that you can recover between 40 or 50% of the energy, which is a lot. And at the same time, you could also reduce the peak power consumption in the port. So I think that's all from my side. I'm just giving you some of the publications that are related with the presentations I give you today here. And those are other publications that are already released. And I'm right now open for any questions. I want to finalize with this sentence from Albert Einstein, which I like very much. He said, we cannot solve our problems with the same level of thinking that we create them. Thank you very much.
Sorry for that. I was muted.
No problem. It happened.
My question, Josep, to start the ball rolling was for the microgrids on the maritime systems. Where do you design in the redundancies in the control systems? Is it at the bottom level, the middle level, or the top level systems for your control system? And also you're changing in the retrofit perspective, you're changing the weights and the design characteristics of the ship. Are you adding weight to a vessel, or are you removing weight? And what do the shipbuilders say to these types of things?
Yeah, that's a good question. So redundancy, especially we built on the supervisory system, but in some cases also it needs to be done in lower levels. But especially we do this in higher levels. And about the weight, yeah, I will say that that normally when it changes case by case, no? But normally when we take out all those old-fashioned engines and we add the new things, I think that the weight is could be the same, less or higher. It depends on how is the topology. But of course, batteries are still very heavy today. That's why also probably the solution it's going to be still hybrid and trying to have better solutions. Like right now we are talking about having e-methanol for supplying vessels. So trying to get more green fields for that and having hybrid solutions, especially when you go for longer distances.
Okay. Mohammed Ali has a question. He would like to know whether the multi-level inverters are being preferred over the conventional two-level ones. Or do they?
Yeah, that's a very good question. Especially multi-level converters are interesting here. But I will say that it has been fixed at 3 levels. So we have seen that if you go further, it could be interesting, but complexity increases, and then the level of resiliency, it can be questioned. But we can see that a lot of companies are developing 3-level converters, especially for the propulsion system, and it works pretty well. I saw also some development in 5-level. So probably when the industry moves more to this area, it will be more preferable. But as you can imagine, here it's very conservative because survivability it's very important in maritime industry. But yeah, you're right, Mohammed. I can see that 3 level is working very well. And then when you go on this kind of topologies, you can see how filters are also reduced. So also it's a good feedback. Yeah.
Yes.
Thank you.
Any other questions from the audience? I could also ask
Yeah.
Okay. Saman Nasiri is asking, is integrating renewable energy sources to ships such as PV economically practical today?
Yeah, not so much indeed. What I could see is in the case of when I presented the Yatchs, in the case of the Yatchs, they are having PV. You have to imagine that in a yacht, maybe it could be many times stop, and still you could charge the batteries. So I didn't show the same thing with other kind of vessels, and because you need a lot of power. And to achieve high amounts of peak of power, it's not possible with PV. But with this kind of yachts, I can see that there's many brilliant solutions, especially suppliers here in Europe.
Amit Kumar is asking if sensorless control approaches are adopted in Shipboard for power management or not.
Sensorless control approaches, it could be a possibility to have sensorless, but I see the sensorless approach, let's say, more on the propulsion side. So, for instance, ABB has been used this approach for many years. So I believe that it could have potential, especially in the lower levels of control. Yeah.
And Alex Navas had a question about what you think about dispatching power at the secondary level instead of at the tertiary level.
Yeah, I think that's the right thing, because you need the dispatch of power needs to be very fast, because you need to balance all the time the power in the ship. So it needs to be placed in the secondary level, while if you think about energy management, so the efficiency, it can be placed in the tertiary level because it can be still slower. So in our case, it's like you want to prioritize the stability of the system, and that's why the part of the power management normally is placed in the secondary level. So he's completely right. Maybe I don't know if I expressed it wrong, but that's something maybe different as with when we talk about land-based power systems. In this case, as is a totally islanded system, secondary level needs to take care of the dispatching of the power.
Okay.
Yeah. Thank you, Alex.
Okay. So I think we're approaching the end of the presentation for today. Josep, you agree that we can send your presentation out to anybody that wants to see it, or
absolutely
by mail?
Yeah, I totally agree. So and if you have any questions, feel free.
I think we're losing Josep.
Yeah, can you hear me now?
I can hear you now.
Okay. No, I was saying just that I agree that that you send all the presentation to the audience. Indeed, there is no secret there, and we like that people have this information, and they are welcome to contact us anytime.
Again, maybe time for one final question. There have been some questions about Seaport microgrids. Do you have some idea about their availability, or how they will be used, how they will evolve in the future?
Yeah, we can see that this is a major trend, and that's because the the electrical power need in the seaports will increase in the next years. First, due to the need of more electric ships and hybrid, so you will need to charge them, etc. And second, because you will not allow the conventional ships to have their diesel generators ongoing and polluting the area. So for sure, you will need to increase. And microgrid solutions, what will give you is to reduce the peak of power consumption of the port to manage internally the emissions and the efficiency, and at the same time to be able to provide energy to the suppliers. So I will say that this is a major trend.
Okay. Josep, thank you very much for a very interesting discussion. I mean, you've connected some dots for me as well. I would like to say this is our last TITBIT for the year, but we will return next year. So follow our webpage, marlog.dk, in our event calendar, and look at what we're planning for a venue near you. That's all from my side, I think.
Yeah, thank you very much, Ernest, and thanks to all your organization.
Okay, thank you, everyone.